So, last session of the masterclass. It's not going to be too heavy. This is going to be quite easy. And I'm not part of the computing expert, so we'll just show you essentially what I do when I implement my stuff. So feedbacks are more than welcome. Okay. So I prepare a Jupyter notebook. So just Google GitHub Lorenzo Rimella. If you want to run it on Colab, on my GitHub webpage, repository, epidemiology workshop. There is a Jupyter notebook. You click on it. Wait for it to load. Then there is the Open Colab button. Click on it. And there we go. We have our Jupyter notebook. So it's going to be implemented in TensorFlow. So hopefully you won't kill me. It's not JAX. But the same stuff can be, of course, written in JAX or in your favorite language. Yeah, I can, but I don't know if it's better. Look at this, Tamas. Yeah. Thank you. So I don't know if you want to maybe here. Anyway, so first thing, we load the libraries. That run anyway. Okay. Boom, boom. Okay, this is just to check that we are using the GPU on Colab. And I can zoom. Yeah, that's a good idea. So is it just? Is it good enough? Okay, so there are the sort of first part of the notebook is just about essentially TensorFlow, what to do, what not to do, the commands. I'm pretty sure that you all know this stuff already. So we're working with Tensor. So the way you create a tensor, for example, is by just giving it a list. And you just use this command, convert to tensor, list, and then you specify the d type, okay? You do that, you create your tensor, or you can just use a NumPy array and then just give the NumPy array and it will infer the type of the NumPy array, okay? And of course, you cannot do operation between, tensors that are not of the same type, okay? Okay, so to actually do operations between tensor, we need them to be the same type. So we need, to convert it to, the type of the other tensor. And then, of course, we can do all the operations that we want. We can do element-wise sum, element-wise product, element-wise divisions, and all the, other operations that, you can find, in TensorFlow. And you can just, Google it if you're interested. Okay, so of course, we are not generally working on small tensor, but also on multidimensional tensors. So I will just briefly also talk about what to do when you have, lots of dimensions. So a very useful operation to do is, for example, this reduce sum operation, where what you do is just you choose one of the dimension, you do just a sum operation on that dimension, and you kill that dimension essentially. So, for example, in this case, I'm creating these, 1000 by 10 matrix. Then I'm looking, at the first dimension, which is 1000, by saying axis 0, and just doing, a reduced sum, which is essentially collapse the first dimension, okay, and create a 10-dimensional vector. And there are two ways of doing it. One way is by just doing this, which will actually kill the dimension. And the other way is to use this command, keep dimension equal to true, which will essentially, instead of giving you a 10-dimensional vector, will give you a 10 by 1, 1 by 10 dimensional, matrix. So essentially, it's just a question of keeping or not keeping the dimension, which you will see that will be useful if we want to use the broadcasting. So, do you know what broadcasting is? Probably you already do, but I will just explain it real quick. So, the way Python works is that if you have like vector that sort of have the same dimension, and then you have like a dummy dimension, we'll just replicate that on that dummy dimension. Okay, so for example, we have our 1000 by 10, dimensional vector, which we call x normal. So this guy here. Okay, and then what I'm creating here is just the results of this operation. Okay, and I'm keeping the dimension equal to true. So you can imagine that this guy here is a 1000 by 10 matrix. This guy here is a 1 by 10 matrix. And you see that, this dimension is the same, but this dimension is the same, but this one is just 1. And you can imagine that the two things are not really compatible, but you have these powerful things called broadcasting, which essentially what it does, it just creates replicates of these matrix, 1,000 times, and just, allow you to do operation on also these, with, these 1,000 by 10 matrices.
Yeah, but did you specify that you're broadcasting? Is that automatic?
It does it automatically. So, by
Dangerous.
Huh?
Is it not dangerous to?
Yeah, so you have to be careful.
Okay.
Of course. Yeah. Okay. So
Follow. Say the dimensions are not directly compatible. So if your second tensor was like 1 and 3, and you should.
yeah, it will give you an error.
Okay,
So it has to be 1. So it has to be 1. It won't work if it's 2. So this guy here. Huh?
So if it's not divisible indefinitely, because saying is unless one dimension is exactly 1.
It has to be 1. Yeah, it will create, exact copies of that. Because you can imagine that if you have like dimension 2, it's a bit weird what it's doing, right? And you're generally not interested in that kind of, sort of. You're not really interested in the operation. Anyway. Okay, and that was exactly, what I was planning to say. So yeah, you have to, your dimension has to be 1, essentially. Okay. Yeah, exactly. So yeah. Okay, so so yeah, and of course, you can imagine that we can also go a step further and just, even create multiple dummy dimensions. Okay, the broadcasting will work exactly the same. Okay, in this case, I'm creating this. Ooh, maybe I didn't run some of the stuff. Ooh. Should remember to run all the cells, otherwise it won't work. Okay. Okay, so we can create also, these multi-dimensional array. And of course, one thing that we can do if we need to exploit the broadcasting is to use this command called expand dimension. So if you remember, this guy was just 1000 by 10. This guy that I've just created has all these dimensions. And so the sort of compatible dimension are the first dimension of, the big array and the third dimension of the big array. And so what I need to do if I want to do some form of broadcasting is to expand the dimension, one here and one at the end. Okay. And so this is possible through this command called expand dimension, where what you do is essentially, specifying the axis where to expand the dimension. And, once you expanded the dimension, you can use the broadcasting as before. You can do, these kind of operations.
Is it done in parallel or?
Yes. Yeah. As far as you load everything, on your GPU, whatever, everything is on. Okay. Okay. Now, I will use a lot this command because I like it a lot. I'm not sure if it's more or less efficient than broadcasting. So this command is called ainsum. And so what you will do is you will essentially use the Einstein notation to perform, operations that are sort of similar to the one that I showed you before, like the reduction operation and this broadcasting operation. Okay. So imagine that you have two arrays that are, this and this, where you have the first one that is 1000, 100 by 10, 1000, 110, and what you want to do is essentially block the first two dimensions and then do some kind of vector matrix operation in parallel on the first two dimensions. Okay. So what you will have to do is essentially expand the dimension of this guy in here, and then do essentially a broadcasting and then a reduce sum. Okay, so this is generally what you do. But there is also a nicer way of doing it, which is by using this tf.ainsum command. So let's just write what is going on. So we are essentially blocking the first two index of our array, M and N. And then what we are doing is to essentially multiply the dimension, the last dimension, the J one, okay? And then doing a sum on the last dimension. So this is what we are doing. And you can see that if we just look at the indices here of the arrays, our resulting array is going to be this M and I. And, you know, our starting array are going to be these ones. And so, create a new cell. And so this is essentially what NameSum allow you to do. So if you write exactly, you know, this kind of stuff with this common NameSum, and you input, you know, the two arrays that you wanted to give, you just do, you know, the same operation, but just in one. Okay.
You can use ellipses.
Sorry?
You can use ellipses. And then
Yes, exactly. And there is also a shorter version which is doing this. Thanks, Adrian. And the cool thing about NameSum is that it's not just about, you know, this sort of, you know, multiplication and reduction operation, but you can essentially just play with these indices as much as you want. You can do like transpose operation across dimension. You can do just multiplication operation like for broadcasting. And of course, you can also do like, you know, differences and division by just, you know, using like 1 over or minus and stuff like that. Okay. Okay, now quick introduction on TensorFlow probability. Oh yeah, and what Adrian said was essentially that, you know, if you have some kind of dummy dimension, you can also just use this dot operation to make it short. So you essentially can just specify the indices that you're working on, and that will work as well. Okay, but yeah, you have to be be careful with the dot. Sometimes it's a bit confusing and dangerous. Okay, so TensorFlow probability, quick introduction. Okay, so given that we are going to work with epidemics models, we use a lot multinomials and those kinds of stuff. And so there is this nice TensorFlow probability that essentially allows you to create a random variable, and then you will have, you know, methods to sample from those random variable, and also to compute like, you know, probability mass function and stuff like that, and not probability mass function. So one example is, for example, I can, you know, specify my population. I can specify a vector of probabilities. And with this command, I will create, you know, my multinomial random variable, which will have exactly that population and those probabilities. Okay, so essentially, this is unlike, it's like I have, you know, 3 compartments. Okay, and I'm saying I have this population of 102 individuals, and I have a 0.99 probability of being in the first compartment, and a 0.01 probability of being in the second one, and, you know, 0 probability of being in the last one. So once I have this random variable, what I can do is to call the method.sample, and this will essentially allow me to sample directly from. Sometimes there are warnings, but generally just ignore them. So if there is something wrong, please tell me. And if I should I not ignore them? You read them, yeah. But you know, once you read, you know, the same warning like 10 times, you're like, okay. Anyway, so you can call this .sample method, and you will sample, you know, from this random variable, and you can also input, you know, some stuff, and you will sample multiple times from this random variable. Okay, so for example, if I say sample, it will just sample once. If I say sample 100, it will sample 100 instances of, you know, the multinomial, and I can also give you know, a sort of array, and it will sample, you know, the array from the multinomial. Okay, so in this case, I will have, you know, as a result, an array that is big. Okay, I will have an array that is, you know, 100, 10, 10, and 3, which is, you know, the sample from the multinomial. Okay, so. And of course, you know, once I have, you know, sample from my multinomial random variable, I can also compute probability mass function and log probability mass function, which are going to be useful to likelihood and stuff. Okay. Okay, and of course, there is also another big advantage of this thing, which is you can also specify, you know, multi-dimensional parameters, and you will create essentially multi-dimensional variables, and you will sample these multi-dimensional variables. So for example, in here, I'm creating this Poisson with parameter 100, and I'm sampling, you know, a matrix which is 100 by 10. And then I have this Dirichlet distribution with these parameters, okay, and I'm sampling 110 times. And so you sort of see what is going on. I have a matrix of 100 by 10, you know, populations, and then I have a sort of array of probabilities. I will input these two parameters in my multinomial random variable, and at this point I will have 100 by 10 multinomial random variable with certain population and certain probability parameters. And at this point, you know, if I just sample from these, you know, multinomial random variable and I block the 2 dimensions just to make the output smaller, you will see that, you know, I will have again, you know, my my output. Okay. Any questions? And of course, yeah, I can do all the stuff. Okay, compartmental model. So I think here we might need a brief introduction. So in epidemiology, generally what you want to do is to essentially model the spread of a disease in a population. Okay, and the way you do that is by essentially dividing the population in compartments. Okay, so for example, if we have a susceptible infected remove model, what happens is that, you know, you will start from susceptible, then you will get infected, and then you will recover and get removed. Okay, so this is an example of a free compartmental. Okay, so of course, you know, we can generalize these kind of compartmental models and have n compartments on an n population, and then the only things that you need is, of course, a transition kernel and an initial probability distribution. Okay, so the P0 is essentially telling you the initial probability of being in certain compartments, and then your transition kernel is telling you how you're moving across compartments. Okay, and precisely you have this kind of dynamic. So you're just, you know, an initial distribution across the compartments, and then you can imagine that once we have, you know, our compartment at time xt minus 1, what you do is to essentially do a multinomial distribution according to your transition kernel, and this will tell you essentially all the individuals who transition on the different compartments, and then you just, you know, collapse that matrix and get, you know, your final state. Okay, does it make sense? Everyone with me? Yeah. But of course, you know, so far what I have just shown you is the dynamic of our process, and we are still missing, you know, the way in which we observe, you know, our stuff, our, you know, individuals. And in this specific case, I will just consider a binomial observation model, which is just, you know, looking at, you know, the different states of the compartment and just with probability Q observing, you know, a certain amount of individuals. Okay. So here I have also a draw on the board, so I will consider the SIR case and draw you essentially what may be used in this good way. Okay, in the SIR case, you have essentially something like this. Okay, you are susceptible, then you become infected, and then you become removed. Okay, okay, and you can imagine that if we look on a sort of, you know, time evolution, we have something like this. Okay, and then you can either stay susceptible or become infected. And then you can either stay infected or become removed. Okay, and if you're removed, you just stay removed. Okay?
Just to confirm, these time steps are consistent or the same for the entire.
Yeah, so I'm considering a discrete time Markov chain. Okay? Yeah. Of course, you know, you can extend these also in continuous time if you want, but indeed for this specific notebook, I will just consider the discrete time case. And then, of course, what happens is that you have also your emission distribution, which is essentially telling you something like this. We'll have, you know, the observed ST, let's call it Y, YTS, and then you will have the observe I and observe R, and in most of the situation, you just have the observe I. Okay, so just observe the infected because the susceptible won't really test, and they recover, you know, as well. Sometimes you observe also the recovery. Okay.
So I think that what Y represents in this case. So you're saying that Y is basically the number that you don't observe in each of these boxes?
So the Y are actually, you know, the things that you observe. So essentially, you can imagine that if you look at the YTI, your YTI is going to be a binomial IT QTI, where QTI is your probability of testing, the probability of testing infecteds. So essentially, in here you will have the number of individuals in S, the number of individuals in I, the number of individuals in R, and then among those individuals in I, okay, you are observing a small subset. Okay, does it make sense? Any other question, guys? Okay, then let's try to simulate this SIR. Okay. So the first step is sort of easy. So what you do is you choose a population. Okay, and once you have that population, you choose you know, initial probability of being in the compartments. And then you just create your multinomial random variable and simulate from it. Okay, so it's just this. Okay. And of course, we can call a function that we call CR step 0, which just take as input, you know, our population, our probability, initial probability of the infection, and also, you know, the number of simulation that we want to perform. Okay. So for example, in this case, I have simulated 100 times. Okay, 100 initial conditions. Okay, and now the sort of difficult part, so which is simulating these transitions. If you remember when I was specifying the compartmental model, the sort of key point was this K matrix, which I didn't talk much about, but is essentially telling you the probability of each individual doing the transition. Okay, my K matrix for the specific case of, you know, my SIR is going to be, you know, for each individual, the probability of staying in S or going to I, the probability of staying in I or going to R, the probability of staying in I. Okay. So we already know that this guy is going to be this because we just stay in R. But what about the other? Okay. So the sort of I to R thing is again pretty simple because you can imagine that the way you recover is sort of independent from the state of the population. And so you will have something like this. Okay, so this is just everything for the distribution. So where gamma is your recovery rate. Okay, and so essentially you recover with rate gamma. Okay, but then for these row is a bit more complicated because the way in which we get infected actually depends on the number of infected in our population. Okay, so the more infected we have, the more we become infected. So we'll have something like this. Okay, so in this specific case, what I'm considering is I have a transmission rate beta, and then I just look at the proportion of infected in my population. Okay, so you can see that the more infected I have, the more likely it is to become infected. Okay, so the next step is now to build essentially this matrix. So I will choose a beta, I will choose a gamma, and then I will just simulate a X. Okay, which is just my population state. And then what I want to do there is just to build that matrix, but we'll build it in a sort of smart way that will allow me also to have, you know, sort of multiple simulations and multiple parameters. Okay, so you can imagine that if I have a beta, this beta can be, you know, unidimensional, or I can have, you know, multiple betas. Okay, so in this case, I'm saying the beta is going to be, you know, a vector with, you know, P elements, okay? And then the X is going to be an array where I will have, you know, an S index, which will tell me, you know, the number of simulation that I do, and P, which will tell me, you know, the number of parameters that I have, okay? And I will use my ainsum command to just essentially build this thing where I have also my index for the parameter and my index for the simulations. Okay. So essentially the idea is that, you know, you will just want to create matrices that are going to be, you know, 3 by 3. Okay. But then you have also a simulation dimension and a parameter dimension. Okay. Is everything clear, guys? Okay, so I will just create this function, which will essentially take, you know, a beta, a gamma. Remember the beta and gamma, you know, are vectors, and then an X, which is going to be an array, and will output, you know, these sort of multi-dimensional arrays of matrices.
Wait, sorry, what is the parameter again? What is?
So you can imagine that if I want to, for example, I don't know the parameter, okay? So if I want to, for example, do a Parseval Bayesian computation, I want to try multiple parameters and multiple simulation with it. So what I can do is to essentially sample multiple betas, okay? And do in parallel, okay, simulation from the multiple simulation return. Okay, so at the end of the day, you will look just at the sort of unidimensional beta, and all the others are just parallel simulation of other betas. Okay. Okay, so so now let's simulate the increment. So what happens is we'll start with an xt minus 1. We'll create our kernel. Once we have our multidimensional kernel, we will just, you know, do our multinomial random variables. Once we have simulated from our multinomial random variables, we will have all the increments. So essentially, all the individuals that stay in S, all the individuals that, you know, from S go to I, and all those kind of stuff. And once we have all those intermediate transitions, we will just essentially sum the individual that, you know, stay in S with the individual that moves to S, which is not going to be anyone. And so this will give our next S. For I, we'll just sum the individual that stay in I and from S move to I, and, you know, all those kind of things. And that's just essentially collapsing the matrix that we have generated with our multinomial distribution. Okay. Okay, and so we can just generalize this thing, of course, in a function, which is going to be our seer step t, and which will take as the input, you know, our beta, our gamma, and our state at time t minus 1. Okay, so now the last thing that we need to do is to simulate the observations. Okay. So again, we have our xt, and what we want to do is to essentially look at this compartment parallel, give a q to each of these compartments, which is essentially the probability of testing the different compartments, and just, you know, simulate from our binomial distribution. Okay. Okay. But I mean, here there is also a sort of extra step, which is taking care of these SMP dimension, right? Because you can imagine that if I want to keep this kind of situation, okay, it's not enough to just look at Q, because Q is going to have, you know, this parameter dimension, and you also to expand on the simulation dimension. Okay. So what I will do is to essentially create copies of the same Q on the simulation dimension, and then just run these by. Okay. Does it make sense, guys? Of course, we can write our function as usual, and now it's time to simulate. Okay, so we have all the ingredients because we have the step that will simulate at time 0. We have the step that transition from time t minus 1 to time t, and then we have the step that actually, you know, give us the observations. Okay, so let's start maybe with the dynamics just to show you how it works. So we'll use this scan command, which we already seen in, you know, multiple times during the master class. And what happened with this command is essentially you create a body function, which is going to be iterated, a number of times that you decide here, okay? So you will iterate that, function, that body function with a certain input, and then that body function will give you an output, which will be pasted sequential, okay? So if I run this scan command, on this set of index, so from 1 to 100, with this initial condition, what will happen is that it will paste x1, x2, x3, x4, x5. All those kind of things. Of course, this is not parallel in time, okay? So it's a bit different, okay, compared to what Adrian was saying before. Okay. And of course, we can collect everything in our compartmental model thing and create, our function, which take as input, the sort of dynamic parameters, the emission distribution parameter, the number of time step, and the number of simulation that we want to perform of our compartment. Okay, and we can JIT compile it. Okay, so this is will just consist of, essentially creating some initial conditions, then create our body function, which will actually output, our xt and our yt. And then the scan command will automatically create our array by pasting, all the output from the body function. Okay. One thing is that it will not include the initial condition. So if you want to also output the initial condition, you need also to sort of concatenate. Okay. So let's do this. And this is going to be a bit slow because JIT compiling. Okay. So the first sort of way that the first time that you run is going to be slow. And then once it's done, it's fairly fast. But in this case, I'm just essentially, so one of the problems is also that I'm giving this as a input. So whenever I change the number of simulation, I have to JIT compile it again because I'm changing the dimension. Okay. But it will be.
Why do you JIT compile? Like JIT compile is essentially using XLA backend.
Yeah.
Versus the standard CUDA backend that we tested.
Yeah.
But if you do the TF function, it could also be a JIT compilation, but just not using the same backend.
Okay. But isn't it this faster?
Not quite true. That XLA optimal is much more heavy than graph mode execution.
No, that's a graph. So if you do TF function without the JIT compile, it is a graph.
It's graph. Yeah, but that one optimal is the computation that's heavily that's a big computation.
The linear algebra computation. So it's
And everything else.
It's not the linear algebra. One of the benefits of not using the JIT compile is so that you can actually use arrays of different sizes.
Right, but if you do that,
Yeah.
So yeah, graph was an action. So
So I guess maybe you want to do this. You don't want to do this when you are essentially running this function for lots of different number simulations. But if you are actually running this if you actually fix the number of simulation, like we will do in ABC, okay, and you run this command a lot of time, you actually want to do stuff. Yeah.
Just because it made
Yeah.
like if you change it to compile, that's why.
Yeah. Anyway, so this is one single simulation. And you can see what's going on. So this is our hidden state. So this is going to be our number of infected. You see that will increase and then decrease. This is going to be our susceptible that decrease. And these are our removed that will just increase. Okay. And these are the observations. So in this specific case, I fixed Q to, what is it? Yeah. Thanks. So it's essentially, I'm setting the Qs on X and R to 0. And the Q in I to 0.1 was it? And so I'm essentially observing about 10% of the infected. Okay, so that's essentially the meaning of this curve here. And of course, you can imagine that we can JIT compile this again with for example 100 simulations, and take again some time for the first compilation. And we can simulate in parallel 100 simulation from our model. It will look like this. Okay, and of course, multiple observation. Oh, why is it not loading?
Yes, it's mouse.
There we go. Okay, compile, and you can see that if I run it again, boom, okay, way faster. Okay, so, and now you remember that, so this is essentially exploiting the simulation dimension, okay. Oh, yeah. So this is exploiting the simulation dimension, but what I can do is also add the parameter dimension. So in this case, what I can do is, for example, create 3 initial distributions that in this case are the same. Okay, then I can create 3 different betas. Okay, and then I can create 3 different gammas that in this case are the same. And so what I'm actually doing by essentially running this kind of stuff is I'm going to simulate from 3 different SIR model with 3 different beta parameters and all the other that are the same. Okay. Well, of course, I need to git compile it again. Take again around 20 seconds. And it will look like this. So essentially, you see that we are using beta of 0.1, 0.3, 0.9. So essentially, you will have with a big beta, a very quick epidemic, okay, with a medium beta, epidemic that we sort of already observed, and then with a small beta, just an epidemic that is flat, so very number of infected. Okay. And again, the second run is fast, okay? Not that fast. Is it? Is it a 0? Yeah, it's a 0. Okay. Okay. So, do you want a break or should we just finish early? Yeah. I mean, it's quite light, right? Compared to Adrian, talk is very light. Okay. So inference. So what we can do is, for example, vanilla ABC, and essentially, simulate parameters. Given those parameters, simulate observation. In those observations, compare the observation with the observation that we observe, and then just reject or accept the parameters. Okay, essentially this stuff. Okay, in this specific case, I'm just considering essentially for each parameter multiple simulation, and I do essentially the expected Euclidean distance from the observation and just accept or reject according to a threshold. Okay, so if my observations are close enough, I will accept the parameters, otherwise I will reject it.
In this case, your parameters are beta.
In this case, the parameters are Q, beta, and gamma, but we'll just consider beta. Okay, of course, you can do it also. The ABC won't work well with loads of parameter, but because. Okay, so we simulate the data, which are going to be the one that we'll use in our ABC. And then we just do exactly what I just told you. So we'll create a simulator, okay, which will just essentially, where we'll choose the number of ABC sample, okay. Then we'll, given that I'm just interested in beta for the sake of simplicity in this notebook, I will just create copy of the same initial distribution, copy of the same gamma, copy of the same Q parameter of the initial distribution, and then I will just essentially simulate randomly collection. Okay. And you can see that, what we are doing here is I have my observations that are the one that I want to compare with, which are going to be essentially, the number of time step and the number of compartments, and then I just expanded the dimension in between. And then the simulation from the ABC, which are going to be, the number of time step, and then we will have the number of simulations and the number of parameters that I'm considering. So the number of parameters that I'm considering are this 550 is the number of simulation from the model.
Can you zoom in?
Oh, sorry. Better? Okay, so good. And so then what I can do is to choose a threshold, compute, our metric of distance, with the observations, and then accept, reject the parameter according to, if I'm close or not to this observation. And of course, you know, once I have rejected my parameters, I can build, you know, KD, you know, of my parameters, which is pretty bad, right?
Wait, sorry, that projection is on what exactly? The threshold, sorry.
So the threshold is something that you choose, okay, and it's essentially comparing the observation from your simulator with the actual observation. Okay.
What exactly? What is it?
The Euclidean distance. Okay, so you'll have this curve, right? You'll have this curve, okay, and then you can imagine that you have lots of other curves all around, depending on the parameters that you have simulated. Okay, and then what you do is just compute. Okay, let's say that you, for example, fix one parameter. Okay, that is the one that you simulated. Okay, you simulate multiple times with that parameter. Okay, so you will have essentially lots of different, you know, curve of infection. Okay, then per each of that curve, you will compute a sort of cumulative over time Euclidean distance with the actual observation.
Okay.
Okay, then you do the mean, so that's the expected Euclidean distance with observation.
Okay.
Okay, and then according to your threshold, you will accept or reject.
Okay. Okay.
Okay.
But I need the observation of how many people are in each of these
Yes.
apartments at each moment in time.
Sorry.
Is
Yeah.
it-
Yeah. Exactly.
Yeah.
Okay. Okay. So, of course, you can imagine that the smaller is the threshold, the better will be our, you know, accept or reject, because we'll be selecting, you know, parameters that simulate closer and closer to our observation by something that is quite hard to do at the beginning, at least. Okay, so what we will do is to essentially sequentially decrease the threshold. So we'll start by simulating, have our KDE, reduce a bit, you know, our prior, then simulate again, reduce again our prior, and this kind of stuff. Okay, because now what we are doing is just simulating, you know, beta from, you know, 0.
So you gotta change your prior as you.
Yeah, so it's a bit like, you know, you can imagine that now I have this KDE on my beta.
Yeah.
So what I can do is to essentially maybe focus a bit more, you know, on this area, okay, and then simulate closer and keep doing it. So essentially I will sequentially reduce my prior and sequentially reduce my threshold, and I will slowly, you know, okay. But there are, of course, multiple ways of doing it.
You know the prediction percentage, for example, right now with this question.
I mean, you can calculate by, well, why do you want it?
Just know how much you're rejecting, how many,
It depends on your threshold, right?
yeah,
At some point, if your threshold is too small, you will reject everything.
yeah.
Okay, so that's why essentially sometimes useful to sort of sequentially decrease it just a tiny bit at a time. Okay. I don't do ABC though, so I agree that it's not a nice thing to do. So yeah, so essentially what is going on here is I will take my beta sample, okay? Then I will take, you know, the minimum, maximum of this beta sample, sort of expand it a bit to avoid, you know, just making the domain of our prior too small, and then reduce a bit the threshold, and I will keep, you know, essentially peeking around, you know, the true parameter, because I will have, you know, better and better choice of my parameters, okay?
I would say it would be more complicated to do this reduction when you have more dimensions. You mentioned that it is very complicated to do it.
Yes, so it will just fail in 9 dimensions, okay? And but yeah, you see what's going on essentially, right? And just and reducing the threshold at the same time, so it will slowly, you know, go closer and closer to the beta parameter, okay? Then I can look at the final threshold and do a final step with, you know, a fixed prior that I sort of chosen, and that's the sort of final result, okay? Okay, and this was ABC. Now I will talk about something that I like way more, which is this Poisson approximate liking. So why are we doing this ABC? We are doing this ABC because we can compute the likelihood of this stuff. just because it's high dimension, okay? But it's possible to approximate it with, yeah,
What do you mean you can't compute the likelihood?
because it's high dimensional. So you can imagine that, this is just 40%. So the likelihood of
When you say
finite.
When you say high dimensional, like, yeah, not, is it?
I mean, you have n individuals, right, which are 100,000. You have to essentially consider all the possible combination of these individuals across 3 compartments. So it's a state space model, okay, where your latent state space is this, you observe just this, okay, and so you have to marginalize out the latent state space, right?
Is that your state space? So like the marginal distribution is the distribution of all possible combinations. Well, all possible partitions.
It's like all the possible way in which you can distribute any individuals across 3 compartments.
Yeah, your individual, so it's like.
Yeah, exactly. So yeah.
Okay,
Yeah,
okay, that,
yeah.
I mentioning that.
Yeah, in that sense. So essentially, if you want to compute, your T or R1T, okay, you will need to do this, okay. And of course, you can do it with the classical, HMN stuff. You can of course simplify it more, but you will have the same problem again and again. So you can avoid the exponentially in time problem, but you won't avoid the exponentially in population problem. Okay, so it's not exactly exponentially, but it's still problematic.
So you can still compute something proportional to the density, right? What you're using nominal, right?
Yeah.
So you look, you can compute that.
No, because we don't observe the multinomial, we observe this.
This even next is something that I'm just like
Yeah, it's fine. So if we go back, I don't know, maybe I have it here. So yeah, so this is the dynamic, So you have the multinomial dynamic, but then you sum it as well, which is, makes everything way more complicated. Okay, because essentially you have to take care of all the possible transitions across the compartments. Okay. And
but that's the full likelihood of your model.
What do you mean?
That's I don't know what I mean. But I'm just like.
So you want to compute this because you don't observe the exit, right? Okay.
Yes. So okay. So finding out the marginal likelihood of all your observations, I understand is fairly hard.
Yeah.
Yeah. Okay. So that I understand is hard.
Yeah, you can do an SMC.
But yeah, you could do that because
You can do an SMC, yeah, but in this simple case it will work. But if you start, having, so this is, for example, one city. If you're like 100 city, or if all of these are just for the individuals, you will have the same problem that I was, talking about when we were chatting to before. You know what I mean?
So maybe the confusion are all the individuals identical?
In here, they are all like that.
Exactly. So
Yeah.
if you could just keep a count, and then it would just be multinomial. Actually, it'd be quite easy to write down the complete data likelihood, and obviously.
No, it won't be easy.
The complete data likelihood.
The complete data likelihood. Yeah.
And obviously the marginal likelihood.
Yeah.
But the complete data likelihood, you could write down, and so you could just use an MCMC algorithm to fill in the box. But if your individuals are all different, then it's complicated, right? That's what makes it complicated. If each individual has its own preference.
Yeah, just I was thinking high dimensional per time step. You see what I mean? Like I thought you meant high dimensional per time step. It's like per time step is just fine. Right? It's like
Per time step is, I mean, it depends what you want to do, right? So if you want to compute it in a closed form, it's still not fine, right? So if you just consider the finite state space HMM, okay, it's still not fine. You agree with that? I mean, you need to do this, right?
One reason that's why.
Yeah, the one is just. So even suppose that you are somehow able to compute this guy, which you are not, okay? This is still not fine, right? Personally, you probably don't even know something like this guy.
Are you just doing it directly?
I mean, it's not this. That's the matrix for each single individual. It's not the transition from. So the XT.
Okay.
Yeah. So the XT is you can do it for a single individual, but the XT is the sort of numbers of individuals for each compartment, and that's sort of where the problem is.
Yeah.
Does that make sense, Adrian?
Yeah. Now I get it.
Okay. So something that I like a bit more. Okay. Actually, it's quite useful about this thing. Okay, so Adrian showed us that essentially in filtering there are two problems: the prediction set, okay, which is this. And the correction step, which is this. Right? And you cannot really do it in closed form because of just the discussion that we had, so you cannot really essentially compute these sums. But it turns out that if you say that your xt minus 1 is this, okay, then you will have that sort of modified version of the prediction step will be exactly Poisson lambda t, okay, and your correction step with the binomial will be approximately Poisson lambda t. Okay, so essentially here what's happening is I have this multinomial transition kernel, okay? If I modify slightly, and by modifying slightly, it just mean given a sort of, Poisson guess at time t minus 1, I substitute in my transition kernel, instead of the state of the population, the expectation with respect to this Poisson. Okay, and with this, I essentially mean, because this is a vector, right? So it's essentially the independent Poisson on the compartments. Okay. So if I substitute the xt minus 1 with the expectation with respect to this Poisson in the transition kernel, this multinomial prediction, okay, will have a closed form, okay, which is again Poisson. So it's some form of conjugacy, okay? So if I start from a Poisson here, okay, and I use the sort of modified transition kernel where I substitute the xt minus 1 with the expectation with respect to the previous Poisson, I end up again in a Poisson, okay? I can give you the reference to the paper and you will see, the sort of proof of the competency. Okay, does it make sense? Any questions? And then for the correction step, it's a similar story, because you can imagine that after prediction, we have a Poisson. And if we use a Poisson with a binomial observation, so we end up again in a Poisson, or better, in an approximate Poisson. Okay, in a shifted Poisson. Anyway, it's a Poisson. Okay. What's the advantage of this thing is that you will end up with essentially this situation. You will have an x0 that is approximate Poisson, where you just essentially moment match with your multinomial. Okay. Then you will have xt minus 1 that is an approximate Poisson and the t minus 1. Then you will have observation. Okay. Then you have your after prediction, which is going to be approximate Poisson. Then you will have this, which is going to be approximate Poisson. And of course, your likelihood, which is going to be approximate Poisson. Let's put it on the black. Okay. And you can see what's the advantage of this, because essentially we will end up with no simulation, and just computing the parameters of this Poisson. So it's a bit like, you know, what you were doing with the linear Gaussian case. Okay, just a different kind of distribution. Does it make sense, guys? Okay, and then once we have this guy, you know, part over T of, you know, all of these are going to be Poissons, and this will be our approximation of the line. Okay, so that is what I'm going to implement now. Okay, so the first step is to essentially change slightly the computation of our, you know, matrix. Okay, our individual matrix. In this case, we are not taking. Oh. Huh? Zoom in, yeah. Okay. Okay. So in this case, we are not taking the x in anymore. We are taking this lambda. Okay. Actually, you probably don't even need to change it because there are two versions of this. So one is the Poisson, the other is the multinomial. If you use the multinomial, you have to change it. But I guess in this case, you can probably use just the same one that I defined above. But anyway, so let's define a new function where we have, you know, these lambda, okay, which is essentially the rate of our Poisson at the previous time step. And then we build our matrix, okay, given this rate of the Poisson, okay. Okay, then what about our prediction? Well, so far I just show you these guys without really writing anything about them. But it turns out that essentially this thing is just going to be the vector matrix product of your previous rate with your individual transition, where, you know, instead of x you have the lambdas. Okay. Ooh, just give it one. Okay, so just what I need to do here is just a vector matrix multiplication. Okay. And this is the prediction, so we can of course have it in a function. So it's just going to take the lambda, take the k, and then just do the vector matrix product. And of course, I will give again a parameter dimension, but not simulation dimension this time because I'm not using any simulation. Next time. Okay. And then we have the prediction step. And then we have the correction step, the update, where, as I said before, we start from a Poisson because after prediction we have a Poisson, then we have this binomial likelihood, and again we have some form of conjugacy and we end up again in a Poisson. Okay, and precisely we will have a Poisson formulation for you know, our filter, and a Poisson formulation for our likelihood. Here there is a given y1 to t minus 1 missing. Okay, and again you can see that the only thing that we need to do, so here, what I have to do here is essentially this guy is our observation yt, which is going to be a vector, so what I observe in each compartment, plus the vector of ones minus the probability of testing across compartment. And this is the element-wise product with our lambda t given t minus 1. So what's happening is, like, I take my rate after prediction, I sort of scale it according to what I don't observe, and then I sum what I observe. Okay, so this will guarantee that at least in my compartment at time t, I will have the things that I observe, the individuals that I observe. Okay, and then we have, of course, the likelihood, which is just, you know, going to be something like this. Okay, but essentially what I do is just I scale my rate with the what I observed. Okay. Okay. And you can see that again is just, you know, vector matrix operations. Okay, so we define our Poisson update where we have, you know, this lambda tt minus 1 as input. Then we have our emission parameter and our observation. And then we can create the final function, which is essentially applying this operation recursively, because you can imagine that what we have to do now is to scan through the observation, okay, and essentially do, you know, this prediction and update recursively, and we will have, you know, an approximation for our filtering distribution and an approximation for our likelihood, okay? And this is essentially what I'm doing here. And the code is essentially exactly the same as the one that I showed you about simulation. But at this time, we are not simulating from anything. We are just, you know, doing linear algebra operations. Okay. Okay. So we can fix some parameters, take, you know, the data that we have simulated before, and just, you know, compute our multinomial approximation. And, you know, you given, you know, the true parameters, these are essentially the sort of, you know, filtering approximation that we have on our compartments, and you can see that they sort of are very close to the states that we didn't observe, okay? Of course, generally, we don't know the parameters, okay? So what we can do is essentially focus on our beta again, okay? This time, I will just create a grid, okay, on our beta. So you can imagine that I don't know where my beta is, so I just create a grid of beta, you know, in 0 to 1. And then for each, you know, beta in this grid, I will run my, you know, approximate likelihood. Okay? And this is essentially what I'm doing over here. Okay? And what I'm plotting here is the profile likelihood of my beta. Okay, where this is the true parameter. Okay? And you can see how fast this is compared, for example, to ABC. Okay. Any questions?
Distribution compares to the true one. Convergence of the.
Yeah, so we have, it's more like frequentist stuff, but we have a JRSSP paper saying that the maximum of this approximate likelihood is consistent to the department. Okay, so if you compute essentially, if you have your, let's call it E1 B project, okay, if you do the argmax, this guy, okay, we call it theta pal, okay, this guy is consistent in the population size. But essentially, the population, okay, if your population was 80, this converts to your year.
How fast?
I don't know.
So I think I think where you say that you only can be approximated by a Poisson.
Yeah, probably, yeah. Yeah. Okay. Any other questions?
So your approximate filtering that you do,
Yeah.
it's an interesting question. If you could set that up so we can temporarily parallelize, I suspect you
Yeah.
probably will, but maybe
Yeah.
it's not such a big deal given that you're kind of parallelizing in other directions anyway.
Yeah, it's a very interesting question, and I was thinking about that while Adrian was presenting, but I was still listening. So I feel like maybe one of the problems is that when you compute this guy, okay, you're doing this operation. Okay, and I don't know if can you undo these guys, because so essentially the way you compute this scale is by inputting the lambda t minus 1
In the exponential.
in the exponential, yeah. Maybe you can still do it. Iterate.
Like you can just use the long you. Yeah, actually, you can iterate. The lambda t minus 1, you can use the previous so if you do like an iterative version, use the lambda t minus 1 of the previous iteration for that matrix. and it feels like that would be contractive in terms of fixed point. And so you just would iterate to the full lambda t minus 1.
Maybe we can talk about it.
I think you can do it in 2 steps. Like it's not something. It's kind of like the extended Kalman filter, right? Like
Something like that.
minimize.
It's a bit like that if you think about it, because you are essentially substituting the XT with their expectation with respect to your approximation
Yeah, but from the previous time.
from the previous times. Yeah.
Without doing that, you could kind of like say, yeah, I'm just gonna like put anything in.
Yeah.
Right?
Yeah.
It'd be like, okay.
Yeah. I see what you mean. Yeah, I mean, there is also a smoothing algorithm for this stuff. So potentially what you could do is forward smoother and then use the smoother in the case.
As you're pointing, yeah, and that would probably work. You can do that, but
Yeah. Anyway, we can chat about it. But of course, another big advantage about this kind of stuff is that it's quite simple to compute the gradient without this, right? Because it's just linear algebra operation. So you can just use TensorFlow JAX to do the dirty job and compute the gradient for you. So we create our function. And then what we can do is to create our loss function, okay, which is just going to be the minus log up the minus log of our approximate likelihood, okay? And then we can just start from an initial condition, okay? Create our TensorFlow optimizer. And then to compute the gradient, you do the, one thing that I forgot is that you have to specify that is a TF variable if you want to compute the gradient in TensorFlow. So you cannot just use tensor, you need to specify and say, okay, this is a TF variable. So sort of, compute without the gradient in here, okay? And to compute the gradient is a bit more complicated compared to JAX, so you need to do this kind of stuff, okay? And then you compute the gradient in this way, and then you just use optimizer.apply to essentially do your, optimizer update. And in this specific case, I choose, Adam as an optimizer, but you can imagine that you can choose whatever you want, okay?
You actually want to move it.
Don't you?
Also in your tape, if you want to do the experiment in the tape, you can call tape.watch and then like give it just before the loss control.
Here.
You do tape.watch and give it tape and the method is watch.
Right. So is this?
Watch and then pick out. Next, yes, it's tape important.
Okay, I mean, I will trust you that it works. This tape.watch.
Yeah, then if you remove the variables.
Hmm?
If you remove the variable, if you want to use it as a variable.
It will still work. Okay, good to know. But anyway, so what we can do now is to essentially do an optimization, right? Because we can just, sequentially do our gradient descent. So this is the plot of the approximate log likelihood, okay? And yeah, and just see that, sort of converge. Just do 50 times step, just because we don't want to stare at these, long. Oh, actually 40. And then we can plot it, and you see that it's not great, but just 50. This is the beta, yeah. But yeah, maybe it's the initial condition. So what we can do is also to create 100 initial conditions and run 100 times, 100 different optimization just in parallel. Okay, we'll have this lovely plot, psychedelic plot. This is the loss function, yeah. And it's fairly fast also, it's doing 100 optimization, right? There we go. Done. And then we have, of course, our 100 optimized beta. Still not great. Maybe I need more steps. Anyway, that's it. Any questions or we can go. Any questions?
There was a question from Andrea, whether we need to take that function when you have different kind of simulation. So I wonder whether you can create a function, like a list of all the functions for each number of simulations to each of the individuals. Is that a good idea? Or
So do what?
so create a function, create a function for each number evaluation within each of them. And wherever you use them, you just record the collection that you have called before. So I'm not sure whether it was clear.
For each collection of individuals.
No, I mean, there was a function at some point where you have an argument like number of simulation.
Yeah. Oh,
And from earlier, whether it like it was cheating or not.
Mhm.
Where people have it.
Mhm.
And my question is whether it's possible to create multiple versions of that function with equal number of simulations. It would mean like a list or collection, whatever. And
No.
within each of them, whatever we do.
Yeah, I guess you can, and you use something like B map or something like that, right? You apply multiple times. I guess the advantage of doing this is that you have everything in a single array, right? So when you're simulating, you're actually simulating sort of, the big array and just doing everything. While if you sort of, split and do multiple replicates of the functions, might be a bit less efficient. Is it right?
I probably wouldn't carry over several versions of the same function for different sizes. Because the thing is, like those computational graphs, they're actually very intensive. Like the randomly used, you can like half the functions combined lib is a hard. It's hard to click.
Okay. I'm going to say for
Yes, like the actual function. It's used like the whole code in memory within the context of your one setting.
yes, no, that's fine.
So it's a bad idea to do like 15 of them.
Okay.
I mean, if there's more ones, yes.
I can't imagine that cheating is that something like you have a strong time for each variable that associated with the function. But if you keep a memory of the whole session inside that. Okay.
Yeah.
Any other questions? If no, let's go. All right. So thank you very much for joining the masterclass, guys. This was the last session. Tomorrow we are visiting the castle. Okay. I know that Darren is not going to be there, but thank you very much, Darren, again for presenting. Round of applause. Pleasure to have you all here. It was honestly a great event. I really enjoyed it, and hopefully you enjoyed it as well. Okay. Okay, so I think we need to discuss for the next masterclass.
Yeah, it can be quite informal, but we can take our time with it.
Yeah.
Anyone who wants to stick around.
Yeah, if you want to stay, give us feedback, it's be very good.
Let's, either way, give people a few minutes.
Yeah.
There is actually a technique.
It's stuck, right? Let's solve this problem, Adrian, and then look. What's going on?
I'm gonna head off.
Thank you
now,
so
but,
much.
Yeah,
Yeah.
thanks for inviting me.
Yeah.
It's really good fun.
Okay,
I enjoyed
great.
it.
Thank
See
you.
later.
We'll say trip back. Guys, the team's call is stuck. And I don't know what to do. Just leave it. We'll lose the recording though.
Hey. Thanks, is anyway. Okay, my words.
Yeah.
It's tired. This is,
I will leave that for a bit.
I'll not you the group.
Oh, yeah, that's one else. I think I'm not good.
Yeah,
I used to, I tried to get, but, yeah.